So thank you for inviting me to give a talk at GeoZoor online. I hope the next one will be in presence because I haven't been in Nice for a very, very long time. So today I will present to you the result of 5 years, maybe more, of collaborative work between the different institutes that you see on this slide. Where we try to get all the geologists that work in the Central Apennines to agree on creating a fault database so that we could construct a model that goes from the fault database all the way to the hazard estimates. And why this is important is because today in Europe, it's very difficult to find databases that allow this kind of operation. Strategies for the incorporation of faults in seismic hazard assessments vary between countries, and the characterization of seismogenic sources remains thus extremely challenging. We are talking about lower magnitude earthquakes than in California, for example. So the work in the field is also much more difficult. So different visions have emerged. There is one vision that says, well, there isn't enough work done. We don't know enough. We cannot depend on faults mapped at the surface to forecast hazard. So in some respects, it's difficult to the point that in the States, for example, they only consider magnitude greater than 6.5 to model on the faults. So you understand that in Europe, the challenge is below magnitude 6.5. So the second vision is, well, which is the California vision, we need the best knowledge of all geometries that we can have in 3D. Let's all get together, seismologists, geologists, seismic hazard practitioners, geodesists, and see what we can do together. So this kind of collaborative work would be nice to get going in Europe as well, but it's of course much more complicated politically and just scientifically speaking. So we started at our small scale a working group within the framework of the European Seismological Commission, which aims, of course, in a very, very long term to contribute to Vision 2, getting people to work together so that dialogue between different fields can be started and we can improve our estimates of hazard. And we started this work in the Central Apennines some 6-7 years ago. And the idea is to try to propose an alternative to the present day vision that is currently being considered for seismic hazard in Europe, which comes out of this working group. So they claim that, okay, we don't have enough information of the faults at the surface, so they imagine some geophysical considerations, what they call composite seismogenic sources. And so here in the Central Apennine regions, you can see these very long seismogenic sources that they describe as representative of what can happen in this region. And they're inferred structures and they span an unspecified number of individual sources, and they are conceived to achieve completeness of the record, according to them. And this is the type of modeling that is actually presently considered in the SERA project. So they really have a big debate in the Central Apennines, as you probably know, concerning the faults that you see at the surface. Can you really use them to infer what's happening at depth? Well, this working group in this particular region considers that all these high angle faults are a little bit of noise. The real seismogenic sources are blind and they're at depth. And so all these faults that we map at the surface, are they useful or are they not useful for seismic hazard? So what we try to do is already to get the geologists that work in this area together to try to quantify seismic hazard based on the map faults and see what comes out of it. And so the first step was building a database. Wasn't easy, but that's the only way that you can imagine having your work as a geologist being used by seismic hazard models. You need to organize your database. You need to make it sure that it contains the necessary parameters to compute hazard. So this was the first step. And then, as Christoph mentioned, I will talk to you about sheriffs and how sheriffs attacks this database to then produce seismic hazard and risk maps. So how can you do this when there is no consensus in the community? Well, we did it through a series of very debated workshops that ended up having, people like Lucilla and Gerald that did not agree on many things, finally agreeing on 80% of the data. And it was a very fruitful discussion because also the geologists got a little bit better knowledge of what it takes to compute hazard and to construct fault models, how many hypotheses go into constructing fault models. And so to try to make the hazard more visualizable and understandable to people, we thought it would be more interesting to compute hazard and risk at localities. So I will show you not maps, but dots that represent the localities where we compute the hazard and risk. And this kind of group was interesting because it managed to also look back to the geologists to say, okay, given the results in the hazard, this is what I need to do to improve knowledge in the field. And so I will go through this a little bit fast in the sense that the seismogenic, the fault trace database was really a geologist's work. I will just go through it to show you a few elements that are important to understand. Building the faults from single traces to faults. The main objective here was to trace the uncertainties. So you will have, different colors to identify more or less well-constrained activities. And then from the traces, there was a first level of interpretation to draw a fault. So what is a fault was sort of a big discussion as well. And not everybody agreed on the way this particular fault should have been drawn. But in the end, what we did, we had this main object was the fault that the geologists felt was the seismogenic source representative of what's happening at depth. And the structure, today actually the structure changed a little bit from the slide, and in the publication you will see the new structure if you're interested. But it contains all this information that allows you to trace where the information is coming from and why we are considering the different slip rates along different sections of the fault. So this database is really quite something that was developed in the hope that it will be picked up in its structure by other places around the world, so that we can make geological information available in such a way that it's used in seismic hazard assessment. So here, for example, you see we classed fault activity depending on the type of information we had to know whether it was active or not. So the red ones are dated displacements during late Pliocene Holocene. So we have paleoseismic trenches that allow us to tell us that this fault is active, modern earthquakes, seismogenic dating. And then you go all the way down to class 4, where it's the gray lines. You have geologic or geomorphic evidence of potential fault activity, but it has not been confirmed as late Pleistocene. So all of that is in the database, and you can activate or deactivate this salt for your hazard computation. depending on what you want to do. So this is also the database of the slip rates, where slip rates could be evaluated. And the colors stand for different slip rates. Red meaning slip rates greater than 1 millimeter per year. And of course, so you have, as you can see, very variable slip rates in this fault network. And so the code that needs to read the database needs to also account for this variability, spatial variability in slip rates.
How is it, the slip rate? Is it measured? It's a GPS measurement, or it's...
No. This is deduced from geological considerations of terraces. Okay. Ideally, sometimes from trenches as well. There are different techniques used to deduce the slip rates. Okay. Slip rates from geodetic data, we are presently trying to do it, but it's very difficult on individual faults. So we're hoping to be able to do that at some point, but not easy, challenging.
Thank you.
So yeah, we just had a workshop last week on slip rates and how do you deduce them. I mean, it depends a lot on the dating technique that you use. And so one needs to also consider the uncertainties in the dating techniques to propagate that to the slip rate uncertainties that then we propagate to the hazard uncertainties. So it's a whole issue in itself. So we can have another seminar on just how do you compute slip rates. It took us 4 days last week, so okay. So this is it. I did a very fast job of a very long and hard work that Joanna and all the others did to put together this database. But now that it's available, we have sheriffs to try to model the faults and their slip rates, and from slip rates convert them into earthquake rates, which is what we need to do hazard. So what is sheriffs in a nutshell? You have a fault system, you have estimated slip rates. So you have a slip rate budget for your region in the fault system. Then you can decide which kind of rupture scenarios you want to put into this fault system. Do you have just faults rupturing individually, or can you imagine that fault ruptures can jump from one fault to the other, as we have seen? And then we need to impose some hypotheses about the overall frequency magnitude distribution of the final synthetic earthquake catalog in the fault system. So how do we do this? So we have our faults. As each fault, we split it up into sections. Here, you see that usually are on the order of, the length is on the order of the seismogenic depth. And why do we do this? So this allows us to attribute to each section the slip rate that is closest to the measuring point. And thus consider slip rate variability along the faults. And also it allows us to construct different rupture scenarios. So yeah, I forgot, I did have a slide on how we compute slip rates, Francois. So this is one example, you know, where you have dating of the slopes. So here, for example, all this scarp is supposedly produced since 15,000 years. And so these measurements were used to derive the slip rate along the slope. Of course, we cannot have slip rates everywhere. Sometimes, like in Celano, there is, for the time being, no way of really knowing what's going on there. And so it's difficult to know exactly how to model slip rate along this particular fault. In any case, there is a high uncertainty attached to it. So if we look at this Celano fault here, you're seeing it distance along strike and slip rates in the vertical axis. The red are the slip rate measurements, and in the middle, we don't know what's happening. Anything could be going. But what we do, we make, you know, an hypothesis about between the points and interpolate, basically. We can interpolate in different ways. The slip rates deduced from the data. This is one possible interpolation, just linear. You can also just say, okay, I just take the average of the slip rates, which is usually what's done on most faults. Just take one slip rate average for the whole fault. Or you can say, well, no, I think that this is my fault, the beginning, the end, and at the end, my slip rates should go to 0. So you can impose that in your model. And it's what we did for the publication. We impose a 0 slip rate at the ends of faults, which implies that you know where the end of faults are. Big discussion there. So then for the scenarios, you know, the discussion is open. In strike slip environments, it's usually accepted that you can jump from one fault to another as long as they're less than 5 kilometers apart. So we made the same assumption here, which of course needs to be validated. And we're trying to validate that through physics-based models right now. So assuming this assumption is valid, then you can construct an incredible number of complex rupture scenarios. Here I'm illustrating just 2. So in the end, for this particular run, we had 1,200 different complex ruptures that we could explore. And so the final step is saying, okay, when you convert slip rates in this fault system into earthquake rates, what is the overall Gutenberg-Richter shape that you want for this region? So what we do is, you see on the right here, we draw some sort of background zone enclosing the fault system, and then we extract the earthquakes that fall in this zone. This is the Italian catalog of the time. And we compare. These are the rates from the catalog with some exploration of the uncertainties due to catalog magnitudes. And you can say, well, yeah, well, I guess the slope can be a Gutenberg slope. Or you can say, oh no, I see a bump. So let's see what the bump does. I really believe that the bump is real, and let's look at how the bump goes. So sheriffs will obey to your orders. It will follow blue if you say you want a pure Gutenberg-Richter, or if you want a double Gutenberg-Richter. So it's a data-driven choice that we are doing today. The earthquake catalog in this region does indicate a bump. So let's see what it does with the bump. So here we are, we're almost ready to go. We have slip rates for each of our section. We have our rupture scenarios, and we have a shape that the overall seismicity rates that will come out of the model need to follow. The basic ingredients are there. What does Sheriff do? Well, it will go in and explore in an aleatory fashion all the possible scenarios that you have put in your list. And it will consume in small incremental steps slip rate, okay? Until the slip rates of that fault strand is consumed, and ensuring that the overall shape remains what you asked. So this, I'm jumping from this the theory, and this is the result. I have some slides at the end that we can go in more detail for those that are really interested. But really what comes out, you put in input slip rates, given the simple rules that we impose, not all the slip rate gets to be consumed all the time. So this is the difference between what we put in and what Sheriffs manages to consume, let's say. And on the right, you have the misfit So you see that for some faults that are either at the end of the system or in some awkward geometrical configuration, Sheriff has a hard time to consume the slip rate that we presumably want to consume there. But overall, the model is doing very well. We are in the violet colors, and it's managing to consume everything that you've asked it to consume. So what we have through the different systems that we've explored around the world, we usually can consume most of the slip rate. We try to stay below 20%. If we go above 20, 30%, then we need to check the modeling parameters. So this is an important check to make when you are using sheriffs, because it's a discretized world, and so it depends a lot on the discretization parameters. So when we compare these geological rates coming out of the database to the earthquake rates, but you see we're doing pretty well in the high magnitude part of the story. You may think that we are doing over predicting the rates in the lower part of the magnitude. So we could do better. And what you can see here as well is that the green curve presents the mean value, but there is also an uncertainty attached. What Sheriff is doing is going in and exploring many rupture scenarios combinations, as well as slip rate uncertainties. And any other parameters or uncertainty that you may want to explore. So you come out with a mean earthquake rate and an associated uncertainty. So here, for example, we only used one scaling relationship, and it's just representing 3 Sheriff's realizations. But if we had done more, you would have had a more dense distribution of the results. So this is it. What you can do with Sheriffs. So this is a check at the system level, but then you can do a check at the individual strand or section level. So here, what I do, I extract from each section the expected seismicity rates computed by Sheriffs, and I compare it to the paleoseismic information. And so this is was done for 4 sites. We are presently trying to build also a paleoseismic database. That's going to take a certain amount of time as well. To be able to have this kind of information on as many sections as possible, because that will allow to constrain the model even further. So it's doing pretty well in Fucino Ovindoli, Montevettore, Campofelice, but in the Fucino Ovindoli Pezza strand 2, our model is over predicting. So this is the kind of checks that one can do to say, yes, my model is representative of a certain reality. Certainly, I was surprised that it could reproduce just like that to first order geologic seismicity rates are really consistent with earthquake catalog rates and paleoseismic rates. So we believe that this geological information collected in the field for this region is consistent with independent data and should be used to inform seismic hazard and risk models in some future world. As today, it's not really taken into account. So once you have your seismicity rates, the advantage in Sheriffs that we really wanted to make sure that the outcome of Sheriff could be taken and used directly as input to OpenQuake. OpenQuake is, for those that don't know, the code used presently in Europe to compute hazard. And it's become a standard for many institutes around the world as well, in fact. So the output from Sharif describing the seismogenic potential of the sources based on geological information can be directly used to inform OpenQuake formalism. Of course, OpenQuake is just a code. You need to parameterize it. You need to have the correct ground motion prediction equations, and so on. I'm not going to go into details on how one chooses these different parameters. You probably all know that there are, three steps. We've just gone over the magnitude recurrence for each fault. Now we need to figure out which ground motion we would like for each fault, and then compute our hazard curves based on that. So here we'll be considering only fault ruptures, because there is also the background to consider as well, and that can be done. We only consider the Bindi et al. Because that was the Italian star ground motion prediction equation at the time. And we are only considering PGA to make just an example exercise. So given these three elements, we can go from geologically informed seismicity rates to seismic hazard at the different localities. So each dot here represents a locality, and the color represents the PGA value for 245 to 2,400 years return period. So, of course, seismic hazard is highest in localities closest to fastest slip-rate faults. As you can see here, this is the Fucino, and this is the Luni fault. Okay, so not surprising, but also at L'Aquila, because it's surrounded by active faults. So this is sort of a proposal of visualization of hazard that could be useful for people living at the different localities. More useful than maps is my opinion. And so then for each locality, you can actually look individually what are all the different sources that are contributing to hazard, and then focus in on just those sources that matter. So this is the total hazard curve at L'Aquila, describing the annual probability of exceedance of a given ground motion, PGA ground motion. And then each curve represents the contribution of each section that we've modeled. And so here, for example, you can see that for PGA of 0.1, it's you have a less than 10 to the minus 2 probability of exceeding it in the next 50 years. You can also look at, in another way, at how each fault strand participates to seismic hazard at L'Aquila. This is sort of a visualization that we came up with Francesco when we were writing up the paper. And in fact, it's Francesco who proposed it, which kind of shows you as you go up in the seismic hazard level, and then you start having the closest faults contributing to the hazard. Okay, at low PGA, you can have very distant faults contributing to the hazard. So this is just an attempt to portray hazard results in a different way that speak maybe more to people that are not necessarily a hazard model. But so any feedback on this will be interesting for me, from you. So what you can also do is check the frequency magnitude distribution of each particular section that you're interested in. So the Valle del Salto fault, for example, comes out as a fairly normal Wittenbericht distribution, whereas the Paganica San Demetrio is more of a characteristic type of distribution. And then you have Barrete that has something in between the two. So these are kind of results that come out of Sharifs and that can help you interpret the type of hazard that you see. So Another way of looking at it, again, is by looking at with respect to the slip rates, okay? So here, the strands, each strand is colored by slip rates. So the red fault sections are slipping at more than 1 millimeter per year in the model. And the green ones are slipping at between 0.1 and 0.5 millimeter per year. And what we're looking at here on the right is the PGA value at L'Aquila. Okay, so you can see Valle del Salto participation, and here, I don't know if you can read, you can have sort of the contribution of each fault at L'Aquila. So a visualization of which fault is counting in terms of the thickness of the section. So you have the thickness, gives you the degree of contribution to the L'Aquila, and the color gives you the slip rate. And so you can see that you have to go quite far at low PGA values, because all of those faults contribute to exceeding a very low PGA value of 0.017 G. If you go to higher levels, like 0.8 G, then you see that mainly it's the faults that are really, that are really close to L'Aquila, just behind L'Aquila, that contribute with some small contribution from far away, high slipping faults. So basically, we're almost there. Let's go all the way to the end. Seismic hazard is just one step. Then the final step is estimating seismic risk. And so to estimate seismic risk, we have to appeal to other models that make considerations about the failure probability of the structure as a function of the acceleration. So these are called fragility curves in our world. And so we came up with this idea of not doing real risk. We're just considering at each locality a standard two-story building housing of the central Apennines. So it's just risk for one building. It's not really risk. It's called typological risk. So, depending on the age of construction, there are different fragility curves that have been proposed. And so we consider the one just published a couple of years ago by Rosti et al. But like ground motion prediction equations, here there is a very wide variety of models that are out there. Just for illustrative purposes, then, we do the computations, we integrate over the fragility curves. And so when you do seismic risk, you're actually integrating over the whole seismic hazard curve. So it's a more integrative vision of the risk. And so this is what comes out with definitely always contributions from the faults just behind L'Aquila, but a reasonable contribution from this structure. So for the city of L'Aquila, it's important to understand what the structure is doing and what the slip rates of the structures really are. So that is just an exercise that we did. So let me remind you again, today it's just an exercise. I ignored many epistemic uncertainties on scaling laws, the shape of the frequency magnitude distribution. I considered just one ground motion prediction equation, only one fragility curve. So this is more of a proof of concept than actual results. But it's work in progress. We're now continuing to work as a group. As I said, we're trying to build a paleoseismic database for the region. But we think that this database, already as it is, it provides a really interesting means for decision makers if they only use it. Because it really visualizes how what is the risk posed by faults at the local scale. But it's also useful for earthquake geologists to go all the way to the end, because given the results, they can plan on which faults to concentrate on in the future. And so this was actually used as the beginning for the INR Equitime project for planning the next paleoseismic trench sites. So this work that I present today is now published, or not in 20, it's in 2021 by Joanna and myself in two different papers, one more describing the database and the other one describing what I just presented, this kind of workflow. So I'm going to leave you at that. There's certainly a lot of things to do yet. Right now, we are looking at rupture jumps in normal tectonic environments with physics-based approaches. We're trying to refine the seismic component of the fault model using INSAR and GNS. This is done in Grenoble. And then verify fault activity along key faults. And there's already one result is that the Leary fault down here is probably not slipping at 1 millimeter per year. So already that is no longer a red fault, but more likely a blue fault. So I think this is it. You're welcome to join us in the group if you haven't done so already. We have a website. This is the address. And we're trying to make this community grow. We're about 100 people today. There is a very, very active group in Spain where geologists, geophysicists, and seismologists work together and meet every 6 months. So that's a great success story. And we're trying to work with South American as well and other people. So this is it. Thank you for your attention and feedback. More than welcome.